tried to cram it into half an hour. So if you're completely lost, feel free to yell out. Otherwise, we can take some questions at the end. But this is the plan. So I'm going to cover a few of the interesting features of the Rust programming language, some of the tooling you get, some of the sort of core or interesting concepts. And then I'm going to tempt fate and do a live demo and questions at the end. So what is Rust? On the website, they claim that it is a systems programming language that runs blazingly fast, prevents segfaults, faults, and guarantees thread safety. So in the next few sections, I'm going to go through and kind of unpack what each of those means. And so before that, a bit of history. The Rust language, the project was started as a personal project by Braden Hoare at Mozilla in 2006. And then in 2009, Mozilla picked it up, started sponsoring it because they wanted a language to build a better web browser. And they had the issues with C++, and so they started sponsoring it. And then 6 years later, in 2015, the 1.0 came out. And between those, that almost 10 years, it changed and evolved into what it is now. So, systems programming language, what does that mean? It means that it compiles to native code and it lives in the same space as C and C++, and trying to solve the same sort of problems that they try to solve, or why you would use those. But it does so with improved safety, and that means a few different things, but two of the most important ones, I guess, no null pointer dereferencing, so common cause of security issues in C code, and no buffer overflows. And it achieves that through some novel techniques, which I'll get to later. So it was originally designed for these sort of more lower level tasks, and interestingly though, it's picked up a bit of popularity in other spaces that they didn't quite expect at the start. So it's seeing some use in sort of web backends, web applications, sort of thing, and even front-end stuff recently. It can now compile to WebAssembly. So you can compile your Rust straight to WebAssembly and run it in the browser, which is nifty. Someone's building a operating system entirely from scratch, and it also runs on microcontrollers. So you can sort of span the full spectrum of tiny systems to very large systems. So it runs blazingly fast. Here are some benchmarks from the Benchmarks Game website, comparing C, Rust, Java, and Go, which is languages I guess that we're sort of seeing here, except maybe C. This is benchmarks, grain of salt, that sort of thing. This is more just to sort of show where it sits, not to call out any specific performance. The vertical axis is seconds for each of the benchmarks, and you can see a bit of a trend, which is basically that it's usually a little slower than C, sometimes faster. And in every other case, I think it's faster than Java and Go. So that's kind of where it sits.
Presumably lower is better.
Lower is better, yes. Faster is better because less time.
Yeah. Can you really quickly read out what they call the benchmarks are?
They're just weird names. Regex Redux, binary trees, K-nucleotide, Mandelbrot, spectral norm, n-body, faster, reverse complement, some weird thing I can't pronounce, and pi digits. Anyway, moving on. So, how do we get this performance? So, there is no interpreter and there is no runtime. So, it's native code, but there's also no runtime like you do see in something like Objective-C. Memory safety without garbage collection. So there's no garbage collector, and that doesn't mean you have to manually allocate and release the memory like you do in C. It's all done at compile time, and the compiler tracks when the data is in scope and alive, and then when it's out of scope, it gets released. They have this concept of zero cost abstractions. So that's not that something is entirely free. It's just that they have these higher level abstractions that permit you to write at a higher level without incurring a cost. So it compiles down to the same kind of performance as if you'd written it in the lower level style, which I'll show later. Prevent segfaults. This is probably my favorite. So this is a screenshot of Sentry from 3Core, and here we can see over 1,000 different events for things happening on nil. So there is no nil or null or other billion-dollar mistakes in Rust. The creator of null referred to it as his billion-dollar mistake. And so in Rust, this is not a thing ever. It doesn't happen. It can be guaranteed at compile time that this won't happen, and it's amazing. So the other bold claim guarantees thread safety. So it has a strong statically typed type system, and through the ownership model that I mentioned earlier, it's able to track which thread owns a piece of data. And so it knows that if you're sharing a piece of data between two threads, and it can reject that. And obviously, it is necessary to share data between threads, and there are mechanisms to do it. And those mechanisms allow the compiler to still track whether it's being done safely. And so this leads to no data races, so you don't have to worry about this weird behavior you get when you're doing multi-threaded coding. And this leads to fearless concurrency, as they call it. So you can, people have this sort of guidelines about, avoid threads, use processes, or, threading programming is hard and stuff. But with Rust, you can dive in, and if the compiler says it's good, it's going to be good. An example was that Mozilla, building Firefox, tried to parallelize their CSS layout engine, and supposedly failed twice with their C++ code. And in November last year, they released a new version of Firefox that incorporated a built-in Rust version that brought in from their experimental browser, Servo. And this one succeeded. And if you're using Firefox, you're using it now. So a strongly typed stake type system. You do a bit more at compile time, so it's a bit more ceremony, I guess. But you have to write fewer tests, so basic things like function names are legit and all this sort of stuff, and fewer runtime checks are required as a result as well. It doesn't impose any sort of major sort of life-changing concepts. It's not like switching from a imperative style to a pure functional style or anything like that. It kind of mostly builds on what you already know, and it's not particularly scary. It's not object-oriented, so there's no inheritance, but it manages to avoid that using a concept of traits and generic types. So traits are sort of like interfaces in Go and Java, bundles of functions and stuff that things can conform to. And unlike earlier versions of Java, at least, you don't have to type all the types. So it has type inference, which is fairly advanced, and often it will just sort it out and work out what it is. The one exception being functions, where you do need to provide the types of the arguments and the return type. And I think that's mainly just a choice for readability. They decided that it was easier to have a concrete definition of the function. And this allows you to refactor with wild abandon. You can move code around and rename stuff and just hack and slash to your heart's intent, and as soon as it compiles again, it probably works. It's great. So on the tooling front, and this is one of the things that sort of newcomers to the language cite as sort of one of the things I like most. The first one is a tool called Cargo. It has a number of different roles. It's a build tool, so it's responsible for running the compiler for you. You don't have to write make files or any of that sort of stuff. It all works out itself. It's a package manager, akin to Bundler. In fact, it was actually written in part by Yehuda Katz, who also was involved with Bundler. And so this shares a lot of concepts there from that. It's a test runner, so there's built-in support for tests in the language, and it will run the tests for you. And finally, it's a documentation generator, and it doesn't actually do all of these things, but it calls the things that do. Having all of the type annotations allows it to generate documentation pretty well, and then you can obviously add your own extra detail, including examples, and that extra detail and stuff is written in Markdown, so it's quite nice and easy to do. And a nifty side effect of this is any code examples you have in your documentation will also be extracted and run when you run the tests, so you know they're legit. So code releases and sort of release management of the project. There's a tool called a secondary official tool called RustUp, which is sort of akin to RBenv, to manage multiple versions and keep them up to date. So it lets you switch between versions and install and update the versions, and that's kind of necessary because there's a new release every 6 weeks. They committed to this sort of constant rolling release model, but not in an unstable way. So since the 1.0 release, they committed to, okay, this is what it is at the moment, and we're not going to do any breaking changes until 2.0. And so I think they're up to 23 releases now since 1.0 and have so far lived up to that promise. So that makes life a bit easier. So the standard library that comes with it is sort of small but capable. It has sort of all the core stuff you might want to do, sort of file system stuff and this sort of thing, network primitives. But for everything else, there's crates. So it's akin to Ruby gems. People can publish their code, and you can use it in your project by specifying it in the cargo toml file, like a gem file. And one other sort of final interesting aspect of the language, I guess, is its community and its sort of approach to steering the language itself. One thing they started or created was this RFC process that's actually been adopted elsewhere as well now. But what it is it allows anyone to propose a change or addition to the language on a special repo, and there's much discussion happens, and at the end they'll decide to whether they want to accept the RFC or reject it. And anyone can do this, and if it's accepted, then it can then be implemented, in that it will be accepted into the thing if someone implements it. And you, as the proposer, don't even necessarily need to implement it. Like, if it's a good enough idea that someone else likes on the core team, they may do it for you. So that's sort of novel. And the other thing that they've done is they have this sort of interesting thing to watch, I guess, of this systematic improvement of the language and the experience for the people who are using it. So they do a survey every year, and at the start of last year, after the survey, they saw there was a few different areas of deficiencies, I guess, things like IDE support and having a clear selection of crates that are sort of high level, stable sort of thing. It's not high level, completed and stable and stuff like this. And so they had come up with this big roadmap stuff they wanted to do in 2017, and basically systematically worked through it throughout the year, going, all right, we're going to do this, we're going to do this, and ticked it all off. And it's been quite interesting to watch how the project's being run, and also comparing, I guess, to some of these other newer languages that have come out and how they've succeeded or not succeeded in the world. Another one is they're pretty big on inclusion and building a friendly community, and people do note that it's one of the sort of friendliest communities that they've dealt with. They've done a few different initiatives to get people who are new to programming involved, or people who are underrepresented involved, and they're mentored and sponsored to conferences and other things. So I think it's all that's also wraps up in the experience you get when you play with this language. So some of the core concepts. We have functions. They're kind of important. So basic add function, 2 parameters, add them together. The I32 means signed 32-bit integer. And in the second part with the main, assigning the result to a let binding equivalent of a variable. They are immutable by default, so you can't change it afterwards unless you prefix it with the mut keyword. Helps reduce errors. Ifs pretty much look like they do everywhere else. That's not much to say there.
How are you feeling in this room?
I have my hoodie on. Did you see it?
Oh, no. I didn't actually read these. Yeah.
The other conditional thing is match, and it's kind of interesting in that it can match on structure and values. So I'm not showing that in this example, but we'll see it later. What that means is you can match on the particular makeup of a particular variable, and drill down into its structure and its values, and then match on that, and then the right-hand side, you do what you want to do. This is weird formatting because it wouldn't fit on the screen. Loops, pretty standard stuff here too. There's a trait called iterator, and stuff that implements iterator has the iter method or function, and this is the standard for loops. And we have ranges as well. There's also loop and while, which are used less frequently, but one's an infinite loop and one's a do while thing. When it comes to loops and the sort of thing, you can code in either a sort of a functional style or an imperative style, and it's kind of up to you, and sometimes one makes more sense than the other. This is a little code snippet I stole from a friend. And so they're accumulating a result here with a loop, and then returning the result. Can be alternatively written like this, where it's a more functional style, and you get iterator, you map some values, and then you reduce them with a sum. And you'll note that this version has a bunch more function calls, and there's a closure in there, which is denoted by the pipes, like a Ruby block. So two things, and this is an example of one of those zero-cost abstractions. This second version compiles to identical machine code. I checked; it's instruction for instruction identical. So you can kind of work with these sort of higher-level constructs and still know that the compiler's going to sort it out for you. Getting into some of the types that are interesting, enums. So you may have encountered these elsewhere. We have them in 3-core as well, the simple version. So it's a type, and the values represent one of those particular variants at runtime. Notably, these variants can carry data as well, and it can be different data per variant, and that comes in handy, as we'll see later. Structs are the equivalent of, well, the replacement for objects, I guess. So named fields with a type, and you can associate functions with them with the impl block there. Enums can have functions associated with them in the same way, and so that gives you the sort of feel of an object-oriented language. You can call thing dot whatever and make it look like a method, even though it's kind of just a bit of underlying magic for you. Yeah, fun stuff. Option. So this is the replacement for null. So anything that can return either a value or the absence of a value, it returns an option. And so this is an enum with a generic type parameter t. So that allows it to hold any particular value. And the interesting part of that is the value is wrapped in this option. And if you want to get at it, you've got to deal with the fact that it may not be present. And this is how you work around the fact that it may be absent, and you don't get these surprise nils floating around. There's a whole stack of functions associated with option that make it sort of ergonomic to work with. You can chain things together and not have to check at each point whether this thing is missing or not. You can just keep going, and at the very end deal with the fact that it might be absent or not. Similarly, for things that can succeed or fail, things like, for example, opening a file that may not exist, you want to get a bit more information back as a result, which is the same kind of thing, except it has an extra variant, or as an error variant, and they both carry data. So in the success case, you get returned OKT, and in the error case, you get a different value back, and whatever this error type is. And usually that error type is an enum of its own that indicates a particular error. And this combined with match means you can match on a result that happened, and you can say, if it was okay, then extract the value out and do something with it. And if it was an error, you can match on the particular error and handle them separately, or you may just punt it back up and just return it to the caller. So there's no exceptions, and this is kind of how you deal with that. You just return the value, and there's a bit of language support for making that ergonomic as well. So that's the sort of whirlwind tour of some of the core parts of language. It's certainly not all of it. There's a lot more. So at this point, I thought I would try and sort of code a little thing and show you sort of what the workflow's like, and kind of what it's like to have the compiler at your back, I guess. Some people get annoyed by the fact that the compiler's whingy and wants you to do these things. But if you flip your head around a bit and be like, cool, every time it's complaining about something, it's preventing an error. And that's kind of awesome. So the idea of the thing I want to build It's just a simple little command line tool that you pass a couple of arguments, paths that don't have to exist. It'll look at the extension and determine what type of file it is and print that out. So it'll say the Rust file is Rust and the Ruby file is Ruby. So here we go. All right, so that's the editor and this is the terminal. We'll start off with creating a new project. So Cargo helps us out here, so we say Cargo new. We'll make this a binary and not a library, so bin and demo. I've done this before. Cool. All right, so go in here, have a look at what it's created. It's got the cargo toml, which is the equivalent of the gem file, and a little main Rust file. I'll just cat the cargo file just for the hell of it. It just defines the properties of the package, and we would list our dependencies after that dependencies block, but we won't need any of those. So if we go to the right place,
The whip branch.
all right, so it has helpfully created a main function, which is where our program will start, and a little message. Print line is the sort of puts equivalent, and exclamation indicates that this is actually a macro. You can kind of ignore that, but macros exist. They are not macros like you see in C++ and C, where it's sort of random text substitution. They're what they call hygienic macros, where they have to still conform to a certain syntax. And it means that you don't get into some of the crazy people defining their own syntax and things with macros. But they can help out with certain things that get tricky, or reducing repetitious code. You can kind of generate code with the macros. So we want a thing to look at a path and determine what file type it is. So that sounds like a fairly good candidate for a function. Classify path, and we will take a path, and the ampersand indicates that this is a reference. It means that we're being lent this value as opposed to taking ownership of it, and this is how the that whole lifetime and guarantees about ownership get tracked by the compiler. And we want to return a file type, so something like that. And path is from the standard library, so we'll pull that in from the path module. SVP. And file type is a thing we're going to have to define. It's obviously a file type is one of several variants, so it sounds like a candidate for a file type, enum. And we'll start off with just Rust, and we can return that here, but that's wrong. The returns are implicit, like in Ruby. You don't have to use the return keyword unless you need it, so we don't have to do anything there. And like any good code, we should have some tests. And in Rust, the unit tests, you write them directly in line with the same code that you're testing. You can move them out if you want, if there's too many or whatever, but this is sort of the convention. And it has a side effect of being in the same module, so there's a whole bunch of stuff around visibility, because you can export functions that are visible outside your module, and then you can have private ones inside it. But your tests can see all of them because they're in the same module. And that can be helpful because you can actually test the private functions without having to jump through hoops. And it encourages you to break things up into smaller functions because you don't have to worry about only testing the exported one. You can test the little bits in between. And I know there's people that argue that that's a bad thing, but I think it's actually probably good. So we want to classify Rust. And this assertEq is a macro that asserts that two things are equivalent. And we want to classify some file that's a Rust file, and we expect that to be the Rust variant of this enum, and so that's that. Now let's run the tests. So my friend Cargo run the tests, and it's going to explode with many errors. So. Cool. All right. So the first one is that I've passed a string to this function, and it's expecting a path. And you can see down further here that it says expected type blah, found type string. So that actually was a mistake on my part. I did not mean to do that. So we will add that one in. Start new. And do it again. And it's still going to blow up, but hopefully with errors I'm expecting. So two things that have happened here. The first one is that it doesn't know how to compare a file type to something else. And it's saying that it's missing the implementation of this partially Q trait. And so the gist here is that being a systems language, it doesn't generate code for you that you may not need. So if you never have to compare two of these things, there's no code to do that. And if you want it, then you can add it. And similarly, when you are comparing these two things, if they happen to be different, it wants to be able to print an error message and say, I got this thing, and I got, I expected this and I got this other thing. And to do that, it needs to be able to format this type, which is not really, it has no actual data. It's just a variant. It needs to know how to do that, and that's this format debug trait. So you can implement these yourself, but for these common ones, you can actually just ask the compiler to do it for you. So we say we want to derive the debug trait, and it will come up with a default implementation that's probably fine. And we want to derive this partially Q trait to make it comparable, and then we run the tests. Now it is happy. So it's complaining about this unused argument as a warning to the function because we're not using it yet. We're just returning the fixed value. So in the interests of doing something useful, we probably should add another variant. So we add TOML into this. And now we need to deal with actually determining what the actual type of file is from its extension. So if we have a look over at here, this is the documentation. And this comes with it when you install it, so this is all local. If we look for extension, type it right, there's a path extension. And so this is the sort of documentation you get in the standard library. Most of it's quite well documented. It's not just the function definitions. Most of it has a decent explanation and examples. So in this one we can see that it's returning an option, and so it will return the none variant of the option when there's either no file name or there's no dot in the file name, or it begins with a dot and doesn't have a dot after that. Otherwise you'll get the bit after the last dot. So that's cool. This OS string is I'll kind of gloss over it a bit, but it's different to a normal string, and it's because that the representation of a path varies by operating system. So for example, Windows is in some 16-bit Unicode format, and others use other formats, and it abstracts that away, and you can not worry about that for now. So our path extension, so we can use match to match on that because we have a set of different sort of things we want to match upon, and we will call the extension method function. Function, because it's not object oriented. That's cool. And then we can tell it what we want to match on. So we want to match on RS for Rust, and that'll be a Rust one, and TOML will be a TOML one. Again, implicit return here, so the right-hand side of these match arms will just be the return value. So if we do that and compile it now, it's going to complain. So here is you have to deal with the option. You can't have these magical nil values just sort of floating about. So we need to deal with the fact that this option is present, and that, as I mentioned earlier, you can match on the structure as well as the value. So the structure here is that if the extension exists, it's wrapped in that sum variant of the option. So we will get a sum on this left-hand side that we're matching on. So we can do that. And if we run this again, now it's complaining about the string to OS string thing. I mentioned that there are different types. We'll deal with that. I mentioned that there's a bunch of methods or a bunch of functions that help you deal with chaining things together, and one of them is and then. It takes a closure and that closure itself returns another option, and it will substitute the original one with the one that is returned from the closure. And I'm doing that because the thing that converts the string can also fail. So toStr, which converts it to a normal string, can also fail if it's not valid UTF-8, because all strings in Rust must be valid UTF-8. So that's handled that one. It's still going to complain. Cool. So we still haven't dealt with the null case, like the empty case. So,
The underscore.
the non-variant of the extension. So we have to deal with that. And I guess that means that if that happens, we don't really know what this type is. So we can return some unknown variant, which we can add here.
I think it's uncode.
It's pretty uncode, yeah. Cool. All right. That comma's not required, but whatever. All right. So do it again. Still not happy, because there are variants of this extension that are not these two. So it has an extension, but it is not RS or TOML. So what do I do then? In that case, we don't really care. It's unknown still. And we can indicate that with this underscore and say, there's some value in here, I don't care what it is, but we'll match on it. And we can use the pipe to say these two left-hand sides match to the same right-hand side argument. Okay, so finally, we're happy. And what was that? Yeah. I could, in theory, add a test for the TOML one, but I'm not going to bother. So that's all well and good. We've got a function. There's these warnings on my editor here. It's complaining about a whole bunch of stuff that's not actually used. That's because I'm never actually calling this function in real code. So let's go through that. We want to get the command line arguments, and they live in the std-env module. And as is typical in C sort of level programming, Ruby kind of skips on this for you, but the arguments to the program, the first one is usually the program itself, its name or how it was invoked, which we don't care about. So the arguments we are interested in are 1 onwards. So what we can do is say that we want envargs, and envargs implements the iterator trait, and one of the many functions that you get with that is a skip function. So you can say skip 1 and do that. And again, this is like all these chaining of functions and things that they all get compiled away. It'll just turn into like a for loop where you start with the index of 1, and it's all cheap. So we've got our path out of the args. That's a string. That's a string, and we want to print something out. So that was the same thing before. We can use that debug format that we created before, or had the compiler create for us for the file type. This is This is this says that this is debug formatting. This is the normal string formatting. It'll take any type here, and it will call essentially like a toString on it. So you can pass numbers and whatever, and it's some of the reason why printline is a macro. So we're going to call that function with the path, and we've got a bit of ceremony here, I guess, because we're wanting to loan our values to this classify function and not hand ownership over to it. So that involves various amounts of ampersands, and we're going to loan that thing to it as well. And then the second thing, we can print the path itself. Cool. So if we cargo build that, okay, that's good. And it's also it also runs the binary for you if you want. So we can say cargo run, and we can pass it some files, cargo toml, cargo lock as well, which will be an unknown one. And there we go, it worked. So that's good. So very exciting.
Watch style function?
Is there, sorry?
Like the file watcher style function?
For for running the tests.
Yeah.
Nothing built in. There is a thing that's written in Rust called watch_exec, which will watch a directory and then run arbitrary commands for you if you want, and it does pair pretty nicely. So that was the demo. I didn't want to go too deep. I hope people were able to follow that.